Hello, everyone, and welcome to today's exciting webinar. This is our first webinar in 2019 on emerging topics in geosynthetics. We have 10 webinars planned for 2019, with the first three dealing with shear testing of geosynthetics. My name is Andy Durham. I'm the geosynthetics sales leader for Owens Corning and a board member of the Fabricated Geomembrane Institute. I'll be your host for today's event. Also on the webinar today is Dr. Tim Stark, Professor of Civil Engineering at the University of Illinois at Urbana-Champaign and Technical Director of the FGI. Today's webinar is facilitated and sponsored by the Fabricated Geomembrane Institute, which is an industry-based organization that promotes the use of fabricated geomembranes for a variety of containment applications through its research, education, and technology transfer activities. Factory fabricated geomembranes reduce field welding, reduce installation time and costs, allow modular construction, and provide consistent seam and liner quality. The FGI consists of over 40 industry members, primarily in North America. Today's webinar speaker is Robert H. Swan Jr. Rob is a leading expert on geosynthetic interface testing and helped draft the initial ASTM test method for geosynthetic interface testing. After completing his master's degree at Drexel University with Bob Kerner, he started the Geosynthetics Lab for Geosynthetic consultants in Atlanta. He took the lab private and created SGI with Zehong Yan. After many years running SGI, Rob returned to Drexel University as a professor in civil engineering and continues to work on geosynthetic interface testing. It is great Rob squeezed us into his busy schedule to give our January 2019 webinar entitled Geosynthetics Interface Shear Testing. So a little housekeeping, please feel free, and we encourage you to ask questions by typing into the questions portal of the GoToMeeting environment. We will try to answer as many questions as time allows at the end of the presentation. After today's presentation, the PowerPoint slides will be available on the FGI website at www.fabricatedgeomembrane.com. So with that, let's get started, and we'll have Rob begin. Welcome, Rob.
Thank you for that wonderful introduction. As I said, my name's Rob Swan at Drexel University. I'm excited to be talking to you about interface direct shear testing. I've done a few of these in my time here. And I've been quite involved with the activity at ASTM to develop and promote the use of not just interface testing, but all kinds of geosynthetics testing. Today's presentation, I've got a number of items I want to touch on. I want to talk a little bit about the different methods that are available for measuring interface shear testing. I'm going to talk about the standards of the industry that we have. There's currently 3. I'm going to talk about who's doing the work, who's requesting the work, and when should the testing be done. Seems intuitive, but I think you'll see when we get to those slides where some of those questions may or may not be as clear. Talk a little bit about the accreditation process for the laboratories involved in geosynthetics. I want to go over some of the details and specifics of the direct shear test concept. I'm going to look at, in detail, the interface direct shear test equipment. And we'll spend a bit of time talking about probably the most important part of interface testing, and that's the test conditions. And then we'll take a glimpse at what kind of typical reporting should be done. And at the end, provide some guidance on how to write up a good interface testing work plan. So, as was told, I look forward to your questions. Don't make them too hard, though. I may have to ask Tim to help me out. So, methods that are available. Direct shear is what everybody thinks of for measuring interface direct shear. There's also the torsional ring shear that was developed primarily for soils, and Tim Stark really was a pioneer in the use of taking the ring shear and moving it into the geosynthetics world. And then there was a young PhD student that liked the ring shear and liked direct shear. His name was Art Moss. And while I was at the University of Utah, he developed a cylinder method, which we'll look at. And then there's always the tried and true tilt table. We'll look a little bit at what Pat Fox has done with a pull-out analysis, and then we'll look quickly at a triaxial shear system that I developed in the early 90s. So direct shear method, based on the concept of direct shear of soils. Big fundamental difference is with soils, we usually use the same size shear box, upper and lower box, and the soils maintained within the box. However, just like direct shear for soils, we're only able to measure the total stress strength of the soil. We have no ability to control the pore pressure nor measure the pore pressure. So whatever we're doing to the test, we're manipulating the conditions, but we're still measuring and reporting a total stress. And that'll become important as we get into test conditions. Now, normally on an interface, we're going to use a much larger lower box, as can be seen here if you look at my pointer. So the lower box is generally about 3 to 4 inches longer than the upper box. The upper box by the standard should be 12 inches by 12 inches. And the idea of having the larger lower box is so that the geosynthetic has a constant area as the upper box or the smaller box moves across the geosynthetic. Generally, there's going to be some kind of normal stress application system, airbag or cylinder of some sort, and then a measurement for shear load. And we'll talk a little bit more about the specifics of where that location should be. Generally, then the geosynthetics are gripped. And in particular, we usually like to use some kind of fixation where we're gripping on one end and the other end of the geosynthetic is loose. And that way, that can maintain the geosynthetic will stay flat during shearing. We don't want to get bunching up. So depending on the direction of the shear box, you want to have one, like in this example, I have the shear box moving from right to left. The lower geosynthetic's clamped on the left side. The rear of the lower geosynthetic is free. So as it's moving, it'll always stay flat. And then the reverse occurs in the upper shear box. Here's an example of one of the shear boxes I've designed and built. This is at SGI Testing Services in Atlanta. And this particular machine was designed for very low normal stress. It is a 12 by 12 upper shear box. The lower box you can't see right now is larger. It's in a containment box that allows for soaking and saturation of the sample. You see that we have a normal load cell measuring the applied normal load onto the sample. We also have a shear force load cell that's going to capture the shear resultant of the upper box as it's trying to traverse across the lower box. And then we see a LVDT, linear variable differential transformer, measuring the shear displacement. We can also attach vertical LVDTs to the top of the box to measure vertical movement as well. The next slide shows you basically from the top down. You can see in particular where the piston's located right at the bottom edge of the upper shear box, right where you want to measure shear force. You don't want to measure up further up on the box because you'll actually create a moment on the shear box and you'll get a distorted shear result. Also in this the picture, you can see that the upper box, you can see some of the lower box. So the lower box is actually moving towards the left. The upper box is held stationary by the piston, and the resultant force is measured in the load cell. So then we're thinking about torsional ring shear. The traditional box was set up for soils about 3/4 inch in width, maybe about a 1/2 inch or so, maybe an inch total thickness, 1/2 inch above, 1/2 inch below, in the shape of a ring. And basically, like the direct shear, one box is moved with respect to the other. With the ring shear, the lower box is rotated with respect to the upper box. And this was found to be very useful for measuring what's known as the residual shear strength of soil, which is the ultimate lowest shear strength that can be measured without any volumetric change in soil. So what was interesting is Dr. Stark decided that, well, if that works for soils, what if I modified it to work for geosynthetics? So looking from the top, this is what our torsional ring shear device looks like. There are two load cell proving rings on each side that are measuring basically the force that's causing the torque to rotate the shear box, and there's also corresponding measurement of the circular motion, so you can keep track of how many times the shear box is rotated. The beauty of the torsional ring is you can rotate the boxes infinitely. You can get out to maybe 3 feet of shear displacement if you want, compared to a traditional shear box, which is only good to about 3 or 4 inches for 12 by 12. Here's how Tim modified it. He modified the lower configuration to not be a soil box, but to be a platform where you could glue or fix a geosynthetic, in this case a geomembrane. He modified the upper box so that he could attach, in this case, a geocomposite, and then rotate the one with regard to the other. Now, the one big difference with the torsional shear is that you do not maintain a direction. In direct shear, you're always going to shear in the machine direction or cross machine or however you configure the materials. With the ring shear, you're rotating in 360 degrees, so you're never keeping the same orientation. So there's a little bit of a limitation there, but by measuring it in that way, we're measuring the limit, the lowest shear value, which is very much needed for design. So as I mentioned, the student at Utah State, he said, well, if a ring is good, why not a cylinder? So he designed his system, he actually patented it, to have an inner cylinder and an outer cylinder so that he could rotate the system, but apply now a larger sample on the size of maybe 12 or 14 by 14 inch geosynthetic inside and a corresponding size outside that he could then rotate in a cylinder fashion, just like the ring shear, and measure the torque and therefore measure the shear resistance. And he was able to confine it and apply a confining pressure. Pretty elaborate system. Downside of this is not able to handle very high normal stress conditions. Then for quick and dirty verification, tilt table has been used. I've seen it done in the field on the back of a dump truck where they've laid the geosynthetics out, they put a weight on it and raised the bed of the dump truck until the geosynthetic interface slid to get an idea what that angle is. Well, a little bit more sophisticated piece of equipment here in the lab has a tilt table that rotates up by the angle, a controlled displacement, and then a trigger that catches once the system slides. So you have a geosynthetic on a geosynthetic. We apply the normal load so that there is some level of normal force. Again, this is limited to how much normal pressure you can use. And the idea is that you raise that plate. So here's an example when it's flat. And then as you raise it, you get it up high enough, you trigger the slide. So the only thing you can get from this test is basically the friction angle. You can't really determine cohesion. Looking at what Pat Fox has done, he has taken the concept of the pull-out test and decided to modify that to use with GCLs in particular. And he decided that he would make an inclusion that allowed the ability to attach GCLs to both sides of a plate that was then pulled from within the soil confining and able to measure a very large scale interface friction, but using the pull-out mechanism. And he's had some good success with that. He's also designed a system to use dynamic loading or cyclic loading for earthquake design. And then finally, I was playing around with GCLs in the late 80s, early 90s. And as you know, with GCLs, we're really interested in the pore pressure. So I came up with the idea to take a cylindrical cylinder that we would do in triaxial, but I made it out of plexiglass and cut it at an angle. And I was able to attach geosynthetic to one piece and geosynthetic to the other piece. or GCL, place it in a membrane and pressurize it just like a triaxial system, and then attempt to measure the slide so that we could try to measure the pore pressure as well as the slide triaxially. Again, that had a lot of limitations because we had to take care of the membrane tension that was developing around the pointed ends, and also from a corrected area situation. You went from a clean oval to an obscure oblong type shape, and the math became quite complicated. So that's kind of a review of the type of equipment. The standard of the industry, however, is to use direct shear. And so first standard that came about was we started as I was a grad student here at Drexel in 1986. Took us to 1992 to get it standardized. The original committee was myself, Barry Christopher, Bob Kerner, Neil Williams, and one of his students, I think it may have been Mike Houlihan, sat in Louisville, Kentucky, and started talking about a direct shear standard. It's interesting because I had an 18 by 18 inch shear box that I built. Georgia Tech at the time had a 12 by 12, and Barry Christopher had a 10 by 10. So we didn't even have a standardized box in 87. But from there, we came to ASTM-D 5321, and the latest edition was approved in 2017, titled a standard test method for determining shear strength of soil geosynthetic and geosynthetic interfaces by direct shear method. Follow on after that, the GCLs came about, and they're special, so they said they needed their own standard. So we took a lot of the terminology out of the 5321, put it into 6243, realizing now we had a lot of conditions that we had to address with the handling of geosynthetic clay liners, potentially gripping. So that standard got approved fairly quickly in 1998, and the latest revision is 2016. And that test is for both the internal and interface resistance of geosynthetic clay liners. And then follow on, there was felt a need for a guide to look at the considerations when evaluating direct shear results. And so this guide is now available. It's D7702. If you're not sure what to do with your result that you've ordered or how you might develop a test program. So that's a helpful guide. So who's requesting the test? Well, there should be a number of folks requesting testing. Design engineers should always be requesting to do testing during the design phase. When it moves into construction, the contractors and installers should be looking at it as an MQA, a CQC type of test to make sure their materials are meeting the design spec. Manufacturers have been always doing some R&D type work, product development, and they're also now doing a lot of MQC and MQA work. Owners and owner reps should be doing testing to make sure construction quality assurance is in place, that the product is in fact what's supposed to be there, and you're measuring the interface strength that's required for the design. Then the regulators come in. Some are interested in R&D. In the early days, we did some R&D. Most of the time, they're really interested in the CQA. And of course, if a failure occurs, then they're very interested in trying to understand why it failed. And that's when the lawyers get involved too. So the failure analysis. So the key is that you should do your work up front, do it in the design to try to avoid the lawyers and failure analysis. So who is doing the testing? Well, we have now a number of commercial labs. In the early days, there was only a handful. Now we have a number. They're all third-party independent, because that's what you want. You want an independent result. There are a number of universities, and of course the Geosynthetic Research Institute are doing testing, but more or less as institutional testing, some for research, some to verify or help if there's a situation between one third-party lab and another, GRI can step in and try to mitigate the difference and maybe figure out what the correct answer is. and then manufacturers, as I mentioned. When the testing should be done. I kind of outlined that in the previous slide, but of course, during the design phase, I can't overstress that enough. And that design should be looking at the site-specific conditions. Not just doing a literature search. You can, of course, come up with all kinds of data. The problem with a lot of the older stuff in the literature is not the test conditions weren't provided. You don't know how the materials were prepared. You don't know if they were soaked or consolidated. You don't know what shear rates. So literature can be helpful, but really site-specific testing should be done. And the engineers that are doing that, they should keep a sample of the materials that they had the lab test, because then when they write the spec and it goes out pre-construction, the contractors are going to be searching around trying to find the best deal, and they're going to put in different materials and say, does this meet the spec? So if you know what your design spec was and you can judge the quality of the materials, maybe the alternate materials will work. But you always should have some pre-construction testing. Then you should be requiring the manufacturers to do their own QC, manufacturing checks. And then, of course, during construction, you have to have your construction quality control, quality assurance done. And if something happens and failures occur, please don't let this be the first time you've done your interface testing, because then there's already lots of problems. So doing your homework ahead of time can really alleviate a lot of failures from occurring. So speaking a little bit about accreditation, there's a number of different institutions out there that do accreditation: ISO, Army Corps, DOT. One for the industry is GILAP, and that's the Geosynthetic Accreditation Institute Laboratory Accreditation Program, which is part of the Geosynthetic Institute under the direction of Dr. George Kerner. And this accreditation is really an important accreditation because it's accreditation based on the test. So you got to prove to George that A, you have the right equipment, B, you have the right procedure in place, and you can demonstrate that you can do the test and get sufficient results. And he checks you on an annual basis. He does an annual audit, and then he comes on site every 5 years to verify that you're still doing everything that you say. And in order to do this, each laboratory has to have a quality plan that consists of a quality manual and how they're going to manage all the operations in the lab, and also have a standard operating set of procedures that they use to make sure they're running their tests, whether it's interface testing or tinsel testing, the same way every way. And just in a quick summary, I looked recently, they have over 75 laboratories that have been accredited, and the range of testing has run from 1 test to 150 tests. I think overall they can accredit, I think I saw 230 different test methods out there. So let's talk about the concept of direct shear. This is what we're all here about. So again, it's based on soil direct shear. And the idea is that we're trying to induce a shear failure into our set of specimens. In this case, we have, in this particular diagram, I show a soil underneath and a geotextile around a block in the upper box. But if I was to just isolate this system and make it generally look like that, what we're trying to do is distort the interface and measure the shearing resistance, as we see here, as a function of normal force. So what's going to happen is we don't get a uniform shear distribution on the sample. Of course, we can get a uniform normal stress distribution, and we should check that, which we'll get into when we get into calibration. But you want to make sure the normal stress is uniform. But when we start shearing, it's going to start shearing in the beginning and it works its way back. So it's not overly uniform, but it does create that phenomena of shearing. And so what we typically see in a set of shear stress versus shear displacement plots, we generally see increase in strength till we get a peak, and then we generally see some kind of reduction in shear stress and a leveling off, hopefully, within the limits of the shear box. And if we run this test over varying normal stresses, usually ranging from low to some high pressure over maybe three or so pressures is ideal. Sometimes you'll do more pressures than that. Minimum, you could do a single point, but we'll talk a little bit about that. But generally, we're going to be looking at the peaks, and then what we're going to call, rather than residual for direct shear, we're going to call it large displacement, because we don't know for sure if we have a 12-inch by 12-inch shear box and we sheared the sample 3 inches. It may appear leveling, but we don't know for sure if it's actually the minimum result. And if you recall when I defined residual is the minimum shear strength. So it's safest to report it as a large displacement shear strength and document at what that displacement is. Was it 2.5 inches? Was it 3 inches? And report that. So then once we have those stresses, we can then plot it on our general Moore-Coulomb failure envelope, shear stress on the y-axis, normal stress on the x-axis, and hopefully they'll plot up in a nice way that we can do a nice linear regression and produce a friction angle, delta, for peak, and measure some kind of y-intercept, which we'll refer to as adhesion. When we talk about soils, we usually call the friction angle phi, and we call the y-intercept cohesion. So with soils, cohesion is the internal strength between the soil itself, whereas adhesion is the attraction between a geosynthetic to a geosynthetic or a soil to a geosynthetic. And then plotting, and I know it says residual on the slide, it really should say large displacement strength. Plotting those lower results, we can get a second fitted line that produces a large displacement, friction angle, and adhesion. But please note, as I have at the bottom here, we're still measuring total stress shear strength, meaning we're capturing both the physical strength of the soil as well as the influence of any pore pressure in the soil. We're not able to measure the pore pressure and isolate that separate to produce a effective stress. So let's look at the equipment a little bit. So equipment type, we'll look at shear box size, go quickly through some normal stress loading, shear force loading systems, and in calibration. So there's, I know there's more than 3 machines now on the international market, but in the US, there's generally 3 machines, one made by Geocomp, one made by Durham Geo, and the other by Geotest. And they each, I put these up because each operates under different conditions. For example, the Geotest uses hydraulic cylinders to apply the normal stress, as well as 2 hydraulic cylinders that apply the horizontal or shear force. Whereas the Durham Geo typically now uses an airbag or ad bladder system to apply the normal stress, and originally was using a hydraulic cylinder to apply shear force, but they've now switched that up to using a stepper motor, digital controlled screw drive system basically to apply the shear force. And the Geocomp uses all electric stepper motors to apply both the normal stress and shear stress. So different configurations, and we'll look at what that does in terms of how the equipment performs. So from a point of view of shear box size, the standardized box size is 12 inches by 12 inches. And by the standard, that's the size you should use unless you have 15 times the D85 of the coarser soil is larger than 12 by 12, then you would need to use a bigger shear box. Or if you have an aperture in your geosynthetic that's 5 times the maximum opening size, you would have to use a larger shear box. But generally, the 12 by 12 was sized to be a reasonable size shear box that could cover almost all geosynthetics. The depth of the shear box was determined to be a minimum of 2 inches, though preferred a little bit thicker, but a minimum of 2, or 6 times the maximum particle size of the coarser soil. So if you have a 1-inch soil, then you need a box that's going to be 6 inches deep. So again, we're trying to cover the general soils when we specified the shear box size, and a lot of thought went into that. Now, there is a guidance that says you can use a smaller shear box as long as you can demonstrate that the smaller device contains no bias when compared to data generated on the standard box 12 by 12. So that's helpful if you're trying to go up to really high normal stresses. But you still got to demonstrate. Every time you've got to demonstrate that the result you get on a smaller box matches what you get on the 12 by 12. And generally, we believe that the larger the shear box, the better the test result, because we're trying to reduce any boundary effects. So we should really follow that guidance in the standard. I've seen and I've run tests up to 30 inches by 30 inch shear in size for shear box testing. And we've really shown a big difference with that larger box. And also done a lot of work with the smaller shear boxes when we're going up to very high normal stresses in heap leach pad applications. But again, what we would do in our lab, we would go up to the highest pressure we could do in our 12 by 12, which was usually about 150 PSI. And then we'd repeat that test on a 6 by 6 at 150 PSI, compare the results, and then proceed higher if we needed to go like to 200 or 300 PSI. So shear box size is critical. Applying normal stress, for very low normal stress, landfill cover conditions, it's best to use dead weight, and dead weight can successfully be applied from 50 up to about 800 to 1,000 pounds per square foot on a 12 by 12. Now, if you're down very low in dead weight and you're trying to model a cover system, you would also want to account for the weight of the soil in the box, because now you're down at a very low pressure. So if you had 2 inches of soil times the unit weight of the soil, you would have that as a normal stress and then add any additional load to that. Once you get up over, like say 5 PSI, the effect of the soil weight really isn't as dramatic compared to the pressure that you're putting on. Then I've seen labs switch to a pneumatic cylinder, which is okay. Cylinders work. They can apply a little bit higher pressures, but they usually max out at about 3,000 PSF. So if you're looking, maybe you're good to go with that. If you don't want to do dead weight up to 800, maybe from 500 to 3,000, you could use a pneumatic cylinder. And then if you really need to go up to the higher pressures, you're going to end up with some kind of pneumatic bladder that's going to pressurize the entire 12 by 12. And generally an air bladder system can get you up to about 21,600 pounds per square foot. If you need to go higher than that, you can use hydraulic cylinders, but hydraulic cylinders are useful, but they must be able to relieve themselves. So if you have any dilatation occurring in the soil, it's going to try to raise the normal stress. And with hydraulic cylinders, they're usually a closed system. So you need to make sure that the lab is venting and allowing that pressure to be relieved. And then with respect to some of the machines that are using electric stepper motors, servo control motors are quite effective, but I would still use a dead weight for the low pressures. And in all cases, you want to include some kind of normal stress loading verification system, such as a load cell or a pressure transducer, to make sure that the load that you're applying is what is actually being applied to the interface. When it comes to shear force, generally you're using hydraulic cylinders or a screw drive system. Again, the key is that you want to maintain a constant rate of displacement, very important. A little bit difficult to control with hydraulic cylinders, but can be done. You just need some special flow control valves. Generally, a screw drive, constant rate, constant torque electric motor or stepper motor is going to be your best bet, especially if you're trying to do extremely slow shear rates. And again, you want to make sure that you have a good load cell in place to measure the actual applied shear force. And you need some verification of deformation. So when we're talking about the shear boxes, there's two main concepts out there. There's the traditional shear, and then there's the shear box that are generally built for geosynthetics testing. So the ones for Durham Geo, Geotest, and Geocomp, They usually have a fixed upper box and a traveling lower box. And that traveling lower box is usually the one that they're going to measure the shear force from. Because it's a lot easier if you put everything in line and you measure the shear force and measure the shear displacement, compared to a traditional soil shear box where the bottom box is the traveling one, however you're measuring the shear force off the top box. Fundamental difference is if you're measuring shear force, and you really need to check with your laboratories what machine they're using, generally if you're measuring the shear force along with the traveling box, you're going to have box friction that has to be accounted for and subtracted from the measured test result. Because of the friction of the harness and all that system is picked up by the shear force. In a traditional shear box design, the upper box is held in place by the shear force piston that's connected to the shear force load cell or proving ring, and the lower box is traveling under it. So the only box friction that's being measured is the resistance of the soil or geosynthetic in the upper box as it's trying to slide with the lower box. And just as a note, this is the design methodology that I've used in the design of my shear boxes. So I follow the traditional. So there is a difference, and you'll know because most labs that are using the other machines will report a box friction, and they're subtracting that off. And that friction is going to be a function of normal stress. So what needs to be calibrated? Well, internal friction of the direct shear box should be checked at least every 6 months. Normal stress distribution at least every 6 months. Electric load cells should be calibrated typically yearly, but a minimum of every 2 years. Electronic displacement devices, LVDTs or whatever, should be checked again yearly, minimum every 2 years. And all this connects to a computer. So actually, to do it, you should actually calibrate and charge your computer data acquisition with known voltages in amps to see what it's measuring. And that should be done at least every 2 years. And then of course, all your support equipment. And you have a right as a test requester to go to the lab and request their calibration data. And if a lab is shy about giving it, then I might think twice about using them because they may not be keeping up with the calibrations. So then let's get into configuration of test setup. We'll talk about sample prep, soil compaction controls, wetting, saturation, submerged and consolidated, and then shear rate. So the first thing, you got to determine what you want to test. Should you include the soils and other geosynthetics above and below the interface of interest? Well, that's some good questions. So there's no true complete guidance in any of the test standards other than we suggest that you use the most realistic representation of the field condition. So ideally, it would be best if you're measuring a geosynthetic, say geocomposite to geomembrane, that you put whatever materials are under the geomembrane and whatever materials are above the geocomposite in the corresponding shear boxes, so you're actually getting the load transfer down to the interface through the different geosynthetics to measure what's happening in the field. Now, a purist might say, well, I want to measure the minimum strength, and so I put a rigid plate above and below. Well, of course, that's going to be a minimum, but it's not necessarily going to represent the field. And what we have found is by having the other geosynthetics applying different loads, we get other interactions going on that are either improving or decreasing the shear strength. So my philosophy has always been to try to represent the field condition as best as possible. So then the next question is, should you do a single interface test or multiple interface or multiple layer? Well, I'm going to leave Tim Stark talk about that in an upcoming webinar. But again, thinking about multi-layer is probably more representation of the field condition rather than fixing a specific interface and testing that individually. Of course, multi-layer can give you the system analysis, and if you need to be very specific, you can always go back and do a single interface to confirm the actual design conditions. But I'll let Tim talk more about that. And then the question is, do you maintain the orientation of the sample materials as they're placed in the field. I would say I would do that, but there are some concerns. If you have a soft soil and you place the soft soil in the lower shear box, you're going to get excessive compression of the geosynthetics pushing into the lower shear box. So it's usually better to flip the entire system upside down and put the softer soil in the upper box where you can control it, and put the stronger soil or substrate below in the lower box and stacking the geosynthetics in reverse. However, you still want to maintain the orientation and construction technique that is done in the field. And so that comes to the next point. Do you compact directly on the geosynthetic, or do you compact away? So again, I use the analogy of a geomembrane on top of a compacted clay liner. In the field, the clay is going to be compacted first, and it's going to be compacted at probably a fairly high Proctor value. So generally, under a high compactive energy, you're actually going to put your clay liner into an over-consolidated condition. And then the geomembrane is going to come down and get placed on top. So if you do what I suggested and reverse it so the clay is up in the upper box and the geomembrane is directly under, you wouldn't want to compact the clay directly on the geomembrane. In that scenario, you'd want to compact the clay away from the geosynthetic and place it on the geomembrane. Again, modeling exactly what's going to happen in the field. So you got to give it some thought, and you got to give the lab some guidance. So typically preparation is left up to the testing lab, but don't be afraid to give them the guidance. If you want them to model or do a specific evaluation, you tell them the conditions, you tell them the specific locations on the rolls of material where you want to sample. Generally, if you don't, they're going to take that roll of material and they're going to cut it on a diagonal and sample accordingly. But if you're very interested and want to be specific, don't be shy. Tell them what you want to do. Be clear in your specification. Don't just tell them ASTM 5321. Tell them what they need to do. Most specifications aren't clearly written to tell them what they should do, and their lab is always looking for guidance. Tell them how you'd like to hydrate it, how you'd like to saturate it, how you'd like to consolidate it, if that applies. Remember, the responsibility of the laboratory is to conduct the requested test as accurate as possible under the requested conditions. So if you don't specify what you want, you're not going to get what you need. It's not the responsibility of the laboratory to do the engineering for the project. So I can't overstress that, and I know, being a lab guy myself, in many situations I was put in, and I actually had to work with the engineers and the client to really get a clarification so that the test is done correctly. This is a performance test. So when it comes to moisture and compaction control, the lab should be able to control the compaction to within a plus or minus half a pound per cubic foot, and a moisture condition plus or minus 0.5% of a target moisture condition. So if you want to tell them to compact 95% of modified Proctor at 2 percentage points wet of optimum, you should, with confidence, expect that the lab should be able to do it. However, some labs will try to minimize the thickness of that clay or that soil, and even though the standard says a minimum of 2 inches, I've seen labs do 1 inch and a half inch. And, you know, the idea is, well, that's less material, but the problem is you lose the accuracy of the density or the dry unit weight, because how precise are they actually at measuring the height of that sample? Most labs will control by volume, so that means they're going to calculate the volume they need to put in the box, measure out the required weight of material, and compact it to get to that volume. So thin samples may be okay if they got good control. Generally, I found that once I got below 1 inch in thickness, the volume measurement blew up, and I had no confidence in what I was measuring. And then comes that same question: compact directly on the interface or compacting away. That should be clearly stated in their reports what they're doing, so you know what was done. As I mentioned, with clay liners and high compaction, generally the pressure from the compactors is going to put that clay into an overconsolidated condition. So if you want to think about that, there's a buildup of pore pressure at the interface just right after compaction. So you want to try to best model what you're doing in the field. So here's an example of some Proctor curves. I have a modified Proctor and a standard Proctor curve. This is from a paper that was published in the 90s by myself, where we were looking at the effect of shear strength as a function of compacted moisture content and dry unit weight. And what you can see as we got lower in density and higher in water content, you can see the values decreasing, and that's shear strength. That's the actual shear strength measured at the interface. So compaction moisture is so important, and it must be controlled, or you're going to measure something that may not be realistic, which leads us into then wetting and soaking of the materials. Are you really saturated? Is the field condition really saturated? Wetting, I understand fully. You got, especially in the summer, working out in the deserts where you have a hot day and a cool night. It's just the same as putting a drop cloth down on the field. In the field, if you're going to camping, nighttime it's fine. You wake up in the morning, that drop cloth is damp underneath. That same effect happens. So you can see that migration of water coming from the compacted soils up to the interface. So wetting the interface is okay. It models, and it's putting the water where you want it, right at the interface. But if you're assuming that everything is fully saturated, well, how's it going to get saturated? Well, the water might come up from below, or the leachate's going to come down from the top. But either way, it's going to wet from the top or bottom to the interface. So even though it may appear to be saturated, it may not be saturated at the interface. So you need to make sure you're putting the water where you want it and not just saying, well, the sample is submerged. Because the sample, unless you take good moisture content samples, you don't know really where the moisture is. So the key is to measure the sample interface moisture at the interface. And if you added moisture, then that water content should be higher than the as-placed condition. If you consolidated and you squeezed water out, then again, that water content could be higher. It also, depending on the drainage, could also be a little bit lower because of consolidation. So I kind of talked about this slide already. A lot of labs have learned how to spray the interface. Whatever you do, you should have them control it. In my lab, we used to have a scale, and we used to use a water bottle, spray it, and measure the weight of added moisture to the geosynthetic to confirm that we were spraying it consistently. All right, then soaking. Is it free swell? Is the system going to be saturated before it's covered? Is it going to swell under load? What's the duration for the access to water? Again, I bring up wetting from the top down. Water access is going to come in from all sides on the interface, but not necessarily in the field. So the question is really, what is the model? What are you trying to model? And being overly conservative and saturating it may not be a good reflection either for what's in the field. And we learned that a lot in work out in California, where the water board was so concerned that the clays be tested under saturated conditions that there was a period of time we couldn't get anything to hang on a steep slope. So after some good guidance, we were able to show them by measuring the compression of the clay layer. We could actually see the consolidation occurring and prove to them that the sample actually went and became saturated. So there's a lot of tricks you can do, but it's all based on geotech. So here's an example of a dry condition versus a soak condition. So you can clearly see same interface, significant reduction in shear strength. Again, what is the model? And then in the field, Are you saturated in the field? Yeah, in the lab we can saturate in the field, maybe not. And so there are some regulators that have said, okay, what if we do a combination shear strength of 1/3, dry strength 2/3, hydrated strength or 1/4, 3/4 to try to estimate what the actual shear strength is over the interface rather than just assume it's all saturated. Consolidation, is it a one-time loading? Is it incremental loading? The duration under submerged? The key is when we're consolidating, now we're trying to dissipate pore pressure, but we still can't measure it. All we can do is measure consolidation, settlement. And so what we're trying to do is estimate whether or not we're dissipating pore pressure. This is very important for fat clays, and lean clays and GCLs. We can monitor this. Not all shear boxes have the ability, but you can monitor settlement if you have vertical deformation capabilities. Use log time or square root time. Or you could use some soil direct shear box if you're using a soil and measure consolidation within that. Again, here's an example of consolidated versus unconsolidated conditions. So in an unconsolidated, undrained condition is going to be typically your lowest shear strength. So figure a lower friction angle. And when you're consolidated, again, I'm not using the word effective. I'm not saying effective stress. This is still total stress, but I've consolidated and I've probably dissipated the pore pressure. So then the question comes to submerge. Do you submerge or not? And if you submerge, the lab needs to account for the soil buoyancy, because now you've not only had the vertical pressure of the soil, but now it's buoyant. So they need to account for that, especially under very low normal stress conditions. So I mentioned this, measuring initial moisture content of the soil during remolding must be done, so you verify what you're putting in. Measure it at the interface when you're done testing so you know what the moisture did. Did it leave? Did it come in to the interface? Measure the GCL moisture content. It's going to show the effect of spraying or wetting. It's going to show the effect of consolidation. And I think I hit my 50 minutes. Sorry about that. But remember that shearing is going to occur within the immediate soil and at the surface of the interface. So we want to be conscious of that. And then comes shear rate. I think this is one of the last conditions that we want to speak about. The default shear rate for plastic to plastic is 0.2 inches per minute, and for soil to geosynthetics 0.04. And so they are basically fast shear rates that are going to be considered undrained conditions. You could still consolidate the sample, but it would still be a consolidated undrained with reporting total stress. With GCLs, we settled on a GCL, the geosynthetic shear rate of 0.04 inches. And then for internal strength, we wanted to slow that down to 0.004 to try to say that maybe we're trying to measure and dissipate some of the pore pressure. But in all cases, you need to have a constant rate. And so what is appropriate? Again, you got to think about the model and how to determine the best shear rate. We also give guidance for a drained shear rate, again, not necessarily assuming effective stress, but if you want to really slow it down, there's some guidance where you can go slower, where you're looking at distance to failure and dividing that by 50 times T50, that's measured from the consolidation test using a traditional soil consolidometer, and then putting a factor in for drainage at the interface. The key point is whatever you're doing, the data handling interpretation, these interfaces are fairly well behaved. You should see typically a well-defined peak and a leveling off. If you see results that continue to raise as the shearing is going on, that's probably telling you that you have a geosynthetic that's under tension, so your gripping isn't appropriate. And if you see the data dropping off significantly, that may indicate that you ruptured your geosynthetic, that you had too much tension in it, and then you broke it. So clamping, and I know I didn't speak much to this, I'm going to briefly. The clamping mechanisms have not been standardized. But the idea is that the clamp that you're using is going to provide a higher shearing resistance than the interface that you're testing, and it must not influence the interface you're testing. So I've seen some systems with long pins and nails, and I have seen those nails come into the interface and actually bind up in the system. So the whole idea is that you've got a really aggressive surface that doesn't dig deep into the geosynthetic and allows the interface to shear. So it should be generally well behaved. And we can go back to that guidance document 7702 to get some additional guidance. Your test result lab, test results from the laboratory should be very clear, documenting everything, including load displacement curves, shear envelopes, giving you guidance on the fitted line. They're going to just fit the line to the data that you requested. And in the summary table, they should be very clear, all the test conditions. In this case, what's presented was soil on textured geomembrane. So we just have the upper soil conditions. We have the summary of shear stresses, and it indicates that the samples were soaked for 24 hours. So clearly in a nice summary, you can see clearly what the lab did, and they'll give you specific notes underneath of things to think about.
Hey, Rob, this is Andy. Sorry to interrupt real quick. We're getting close to the top of the hour, which is fine. You got a lot of really good content. I know you got some more slides that we want to get through. Take your time. We'll ask everybody to stay on a little bit past 1 o'clock Central Time. Let Rob finish, and then we'll try to get to some questions after it. So I just don't want anybody to feel like they have to leave right at 1, and Rob, just go ahead and finish up.
Yeah, I only got a couple more, and it's going to be fairly quick, and then we can start the questions. I apologize for the length of time. So just in the level of review, good laboratory report starts with good quality laboratory testing. It's important that there's multiple levels of review, just like a consulting project. So the person reviewing the lab data shouldn't be the person doing the testing. There should be at least somebody else's eyes looking at the data. Does it make sense? Does it smell right? So they go to smell test. And you want to make sure that it's technically correct. So generally, we'd like to see a geotechnical engineer reviewing these results and doing a good peer review to make sure the result is producing the value that is required for the conditions. Take the time to check the results. Technical soundness helps eliminate project delays, embarrassment to the client and laboratory, and expense in retesting. And the next couple of slides, I'm not going to go through bullet by bullet. You can look at them, but these are taken directly out of Fox and Stark's state-of-the-art of GCL testing in 2004. It's a nice set of guide points on contracting for interface shear tests, what the user should require, what the contracting user should provide, who should specify the following, the user, and what's expected. So these are really good, and I tried to hit on a lot of these key notes in my comments, but it ends up that the quality of your test result is based on the quality of the testing and the accuracy of the test requester in specifying the conditions. The same thing, garbage in can be garbage out. If you don't give guidance, the lab is going to do their best and it'll produce a result, may not be representative of the condition. This is a very important performance test. Results are dependent on the conditions. So be careful what you ask for and take the time to properly specify the test condition which are needed for testing. Remember, failure to specify correctly may lead to the failure of the project. And I believe that brings me to a closure for my presentation. Thank you.
Hi, thanks a lot, Rob. I really appreciate it. We're going to try to address some questions here for a little bit. I don't know how many we'll get to, but we'll try to, if you have asked a question and we don't have time to answer it on this webinar, we will try to email you an answer to that question for Rob. So I'll start quickly here. I believe we're going to get a little bit of an extension in the webinar, so hang with us here. The first question I have comes from Dennis Columba, and he asked about the gripping system and how that can affect the results. How far are we away from having a standardized gripping system as part of an ASTM standard?
Okay, so your name was Dennis. Dennis, to be honest, we are not even in discussions at ASTM on a standard gripping system. We are focused right now on just trying to get a good reproducible result, and I know gripping comes to play. We've been doing some round-robin testing really through the GRI, through the accreditation program. What is of interest that's currently in discussion, and I'm going to come back to the first part in a second, is there's some concern about this multi-layer interface testing. Right now, there's no specific guidance in the standard, so there's some that are pushing to say that we shouldn't allow the use of multi-layer interfaces within this current standard because the standard is designed for a single interface where you're gripping specific geosynthetics or soil. There's a contingency of which I'm pushing is that the standard is adequate for it, and we should write another procedure that addresses the proper ability to use multi-layer. Some of the folks want a different standard altogether. But to go back, the gripping is fundamentally important, and it does influence the result. I tried to point to that when I'm looking at the behavior of the test result. If your grip is too weak and you're slipping on the interface between the grip and the geosynthetic and not the interface that you want to test, then you're measuring the grip in geosynthetic interface. You're not measuring what you want. So the grip has to be strong enough to force the failure at the interface, but it cannot be influential in stiffening up the geosynthetic or protruding through the geosynthetic so that it's adding strength to the interface. So a lot of care has to be done. There's a number of systems out there. I personally perfected the use of wood rasps on wood because the wood rasps are sharp enough to bite into the geosynthetic, but they're not pin-like that actually come up through the geosynthetics that I've seen on a lot of needle boards. But there's still a lot of experimentation. Hopefully that answers your question.
Okay. Thanks, Rob. That was a great question, Dennis. Next question comes from Charles Sequanda, and he's got a two-part question. I'm going to try to consolidate it a little bit here. He asks, referring back to slide 30, different manufacturers or makes of direct shear boxes, such as GeoComp or GeoTest, and how they could they lead to different interface shear strengths? And if so, what would be the allowable difference from two different laboratories if they conduct the same test and they don't get the same results? Do you have some insight on that, Rob?
Yes, I do. That's a very good question. And that's the problem that we're seeing in our accreditation program and just trying to get a precision and bias statement. If you've looked at our standards, we do not have a precision or bias statement stated in either of the standards. And that's because we're not able to measure it. The variance is too high. Even for simple geomembrane on smooth geomembrane on non-woven geotextile, you would think everybody would get the same answer. But I've seen data from as low as 4 degrees to as high as 18 degrees on that interface, coming from the different labs in the industry. And we've been trying to figure out where the problem is. I believe truly that some of it is in the way the machines are working, where the shear force is being measured. If you're not measuring at the interface and you're measuring somewhere up where you're getting a moment, you're going to produce a different result. So the problem is, yes, we have some machines out there. There's no standard machine, and we don't have any guidance. It's just like the Proctor test. There's still no precision and bias in compaction and in a lot of the soil tests. It's just one of those tests that is very difficult to do.
Yeah, thanks, Rob, and great question, Charles. I can tell you this, Rob, we've got a bunch of questions. They're all great questions. We're at 5 after 2, and I know we're not paying you by the hour, but if you're willing to stay on and answer some of these questions, we'll certainly keep going. We've still got 153 attendees on the line, so we'll keep going until we finish all the questions, if that's okay with you.
That's fine. I have no time. Yep.
Okay, great. So let's move on. Thomas Brown asks, slide 29 noted shear rate limits to maintain drain conditions, but the test is only for total stresses. How are the strain rates selected?
Slide 29 or 39?
Oh, I think it was 29, but yeah, slide 29, 29 out of 59. And he was talking about, he identified shear rate limits from to maintain drain conditions.
Well, that's a very good question. We have the guidance in there, and I know there's a paper coming at Geosynthetics 2019 that kind of speaks to this a little. I don't think it's appropriate for me to disclose what's all in those persons' papers, but the work has been trying to look at this shear rate calculation, and it's based. I mean, the idea of shear rate 50 times T50 is based in soils. It's in 3080, the shear standard for 3080. However, it's difficult because we have a large box and we have a drainage scenario that's not the same as soil by itself. We have a geosynthetic. It's either a smooth sheet, it's either a continuous sheet like geomembrane, whether it's textured or smooth. Could be a geotextile that can provide drainage. So geomembrane may not induce drainage. It may actually cause a buildup of pore pressure. So we use this factor to try to adjust for the drainage condition. And in the standard, we give some guidance on what that number is. But the biggest problem is, well, there's two. How do we measure T50? So we suggest that you use 1D consolidation for the soil itself. And then we suggest for the displacement at failure to be taken as the peak shear displacement. And so if you do that, that's fine. That's going to give you a little bit more conservative lower shear rate than if you took the failure at the end of the test at 3 or 4 inches. But the other question is, if you're testing the soil by itself in a 1D consolidation, you do not pick up the drainage. So what we used to do in my lab, and we still do, is we measure the consolidation from the big box that includes the geosynthetics at the interface so that we can get a reflection of the drainage. And then use our 50D50, and we still go to peak to give us an estimate. But because we can't measure pore water pressure, we have no idea if we're even drained or not drained. The only thing we can tell is that we get a different shear strength. And typically the shear strength is higher than the faster shear rates. So it's still a lot of uncertainty. I don't know if that answered your question.
Yeah, that's a great answer, and I think that provides a lot of good perspective on that, Rob. A question from Riva Norte. Testing geocomposite drainage sheets. How would you do anything different on the clamping or grips for those when you're doing the shear box testing?
Well, there's two ways of doing it. Are you talking about an interface or are you talking about an internal strength? Because with
I think he's definitely talking about internal. I'm sorry, I should have clarified that.
Okay, so and that's an important point because the manufacturers don't want to use a lot of heat or whatever bonding agent to bond the geonet to the geotextile. And so, I've had geocomposites come in. If I looked at it the wrong way, the geotextile fell off the geonet. So there is a way of doing it, and I would treat it like a GCL, doing an internal strength of a GCL. I would actually cut it so that I had an extra length of geotextile on one side and on the opposite side an extra length of the geotextile, and I would wrap it around a gripping surface so that I could actually apply my normal stress and measure, just like a GCL, the internal strength or the bond breakage between the geotextile and the geonet. The same methodology, same clamping works just fine. And we've also found fairly good correlation with the peel test. that's being done now also with GCLs is measuring the peel and seeing how they correlate to the direct shear strength. If you're doing the interface, I would probably still do something similar with an upper clamp, but on the lower, I would actually leave the lower geotextile free and let it slide against whatever if it's a textured geomembrane or below. And chances are, if the bond is weak, it'll break at that point, and you'll measure the geonet to geotextile interface because that's weaker than the geotextile, the textured geomembrane.
Okay, thanks, Rob. This is a really good question. The asker, Charles Plumridge, wants to know if you can comment on degree of accuracy and reliability of a numerical constant to convert the soil's internal friction angle to an interfacial friction angle between that of a soil and a particular geosynthetic. And so he goes on to specify a constant would be determined experimentally, the geosynthetic by finding the interfacial friction angle between it and the soil of a known internal friction angle, and then a safety factor can be used to make up for uncertainty. Is that something you can comment on, Rob?
I can comment it, but I'll comment it for sure. But the answer is we don't know. But I'll comment it on the form of efficiency. Now, I haven't spoken about efficiency, but efficiency from the point of view of the interface shear strength to the soil shear strength. Because whatever we do with a soil, to say, I'll use textured geomembrane because it's easier, the texturing is going to cause the internal failure in the soil just 1 or 2 soil particles deep, depending how thick the texturing is. But it's going to cause the failure in the soil, as opposed to a smooth sheet where the soil is going to slide on the smooth geomembrane. So we are able to generate a soil strength, but it's not the same strength as if we were doing a direct shear test on the soil by itself, where we're getting a much deeper shear failure. So what I've seen in the years of doing this is that the friction angles of the soil and of the interface under the same placement conditions and other conditions can be very similar. The biggest difference will be in the cohesion versus the adhesion, because you don't get the effect of the deep shear. So generally, soil textured geomembrane, I think you can probably get an efficiency on friction angle, probably 90%, maybe higher. On adhesion versus cohesion, maybe 20%, maybe higher. But it's going to be a relationship to the soil strength and the interface strength. I don't know if you can really nail down, unless you've done extensive testing on a particular soil and geosynthetic. But generally, that's kind of a rule of thumb that I've used. I don't know if that answers the question, but
I think that's a really good insight on that, and that was it was a great question, and appreciate Charles asking that. So this will be not our last question of the day, but definitely my favorite question of the day. It's really a good one from Boyd Ramsey.
Hey, Boyd.
Could you comment for your audience about the relationship or lack thereof between interface shear testing and other material properties such as asperity heights with geomembranes, peel strengths on GCLs and composites, etc.? I think that's a great question, and really like to hear your thoughts on that, Rob.
No, that's a great question. I appreciate it, Boyd. And now Boyd has changed his colors. He's a consultant when he was a manufacturer. So we've had many discussions about that. Well, it all comes to the quality and the distribution of the texturing. So there was a period of time where we thought the more aggressive the sheet, the better the interface strength. And then we started to see a significant decline in geomembrane properties because the core went away, especially on blown film. And so we were having problems with that, but we were getting great interface strength. And then there was this decision to say, let's go to a minimum and say, this is our stock sheet, and this is what we got, and you, engineer, has to work with it. Well, that worked for a little bit, but then the engineers got smart and said, hey, we still need a little bit more than what I would call plucked chicken skin to make sure that we have enough interface strength. So there is a direct correlation, I believe, not only in asperity height, but in asperity density. And I know with the Soil Max folks that they've been pushing a newer liner with asperity density. And I absolutely agree that there is a combination of density and asperity height that works tremendous. We could see that in the Agro microspike sheet that some say you could scratch the texturing off with your fingernail, and I agree. I've done it myself. But when you put that in contact with a geotextile, it's like Velcro. And so that has great distribution for very low asperity. So I think there's a combination, and I know Joe Dove and David Frost at Georgia Tech in the 90s were looking at this with perimeters and trying to establish that. I worked with them a little bit. We published a few papers on that to see if there was an optimum height and distribution that gave us the good interface strength, but also didn't decline or reduce the properties of the geosynthetic. It's still out, and I think there's still a lot to learn, but I'm encouraged that people are starting to rethink it again, because we do need some level, and we need that control that can be counted on, the engineers can count on.
Great answer, Rob. Appreciate that. We've got two more questions. We've still got a whole lot of attendees on the line, so we're going to go ahead and finish those questions up. The first of the last two is from Philip Kraus, and he asks if there's any changes in interface testing for geosynthetics with respect to coal combustion residuals. So are we doing anything different with these direct shear tests if we're encountering ash?
Not that I'm aware of. I've done a bit of ash work, and of course it's easier when they're dry ash because we can treat them like soils, and they behave a lot like soils. If they're in the slurry state, obviously they've got very low shear strength, and you do have to make sure your shear box is watertight and able to handle it. But you just got to be careful in the way you load them. If they're still got a high water content to them, they can become flowable under pressure, just like a GCL can. So you might want to use a stepwise loading for consolidation if you're trying to consolidate, so that you don't squeeze the ash out if it's wet. But generally, the work I've done has been more on the drier side, and they behave quite well like soils. You do have to be conscious of the health and safety issues, the heavy metal content. So the lab should be made aware of what's in the material. And if the lab's not confident or sure, they should test it first from a health and safety point of view. Fly ash generally is more preferred over bottom ash because the bottom ash has the very high residual heavy metals in it. I've worked with both, so you got to be real careful.
Okay, great. And the last question from Anthony Ahmed. He asked if there's a reference index for recommended max slope angle for general soil types and geomembrane materials. I also wanted to kind of add on to that question, Rob. We know that there's the GSI, I think it's technical report number 30, on the database for geo to geo and geo to soil interface friction data. So I think the answer is yes, there is some guidance out there. But I want to ask you, Rob, how much confidence can an engineer use and design with that kind of generic guidance? At what point can you do some preliminary design with that database versus when you really need to go to some specific direct shear testing?
Well, it's a good question, and there's some good value in that. Because it can help if you got a complex lining system, you can start to eliminate intuitively interfaces that are going to be a problem, and narrow you down to some specifics where then you would want to do your more site-specific testing. I would not do a design based on published literature unless you were absolutely confident that you knew the conditions, the soil placement properties, the normal stress, the wetting, consolidation, shear rates. And fortunately now, most papers that I'm seeing have putting all that data in there. In the early days, none of that data was there because we didn't think it was important. But care must be taken in using anything generic, but it can help weed it out. And the other way to do it, and I'm going to allude to Tim talking on the multi-layer, is after you've done that and you thought you've eliminated it, do a multi-layer test and see if for sure the weak plane that you identified in that literature review is in fact a weak plane, and then go back and model that particularly to get your design criteria.
Yep, that's a great point, Rob. Appreciate that. I really want to thank you, Rob. We had a great webinar today. We had over 170 attendees on at the webinar, and we had still over 120 kind of stay with us through all the questions and answers for 20 more minutes. So I'd say it's probably one of the most successful webinars that FGI has ever done. And wanted to, before we wrap up and close out, just a couple ways to become more involved with FGI. Please join the FGI leadership and the overall membership at the 2019 Geosynthetics Conference in Houston on February 10th through 13th at the Marriott Marquis Hotel downtown. FGI will have its general membership meeting at 12:15 p.m. Central Time on Tuesday, February 12th at the Conference Hotel, and all are welcome to join. And please visit the FGI website, www.fabricatedgeomembrane.com, for all kinds of technical information, including plenty of new videos covering geosynthetic test methods. You'll be able to download this presentation and the recording of it there as well, and learn about more upcoming dates for the 10 webinar series that FGI is doing for the remainder of 2019. Thanks again, and a special thanks to Rob Swan for all your hard work and putting on this presentation, and thanks for the audience for bearing with us through today. I thought it was a great presentation today.
Thank you. I really appreciate that.